Okay, guys. Hello, everyone. So I think we shall start. It's already 2 minutes since the lecture should have begun. Welcome back to machine learning course. Today is the third lecture, which will be devoted to linear regression and all kind of things connected to it. So let us start with learning outcomes or objectives that basically a list of things that you're supposed to be aware of or know after the lecture. So we will one more time. I think most of you already did that on the seminar and maybe also on the previous lecture, Evgeny mentioned that the direction for closed form solution for linear regression. We'll try to go through that briefly to make sure that we are all on the same page. We will also be discussing regularization, mainly L1 and L2 regularization with a focus on linear regression, but of course, it is a general concept that can be used not only with linear regression. And we will also discuss what is overfitting, how to detect it, and we'll also briefly talk about validation and cross-validation techniques, and you will then cover them in more details during the practical sessions. So let's start with the first point, with the multivariate linear regression. So as you remember, for every model, to train it or to get to start training, we need 3 components: the model itself, so how the model looks, the cost function that we'll be optimizing, and our training data set. So let's formalize all these 3 components for linear regression. We have our data set, which consists of design matrix X, which has n rows, where n is number of observations, and d columns, where d is number of features. And we also have vector of target variables, which are real numbers. Our model would be just a linear combination of our features. If we consider one object, that would be, by the way, do you see the slide? Let me check. Yeah, now it should be better. Yeah, so for one model, for one observation, that would be just a scalar product. But if we would like to get predictions for all the points in the training data set, or for several points, that would be just the design matrix times the vector of features. And we also have a cost function, which will be for today mean squared error. So basically the average square difference between our predictions and the real values, values of the target variable. We can, of course, also rewrite that in matrix form. So model errors would be just predictions minus the real values of the target. And knowing the definition of Euclidean norm, which is the sum of squared components of the vector, we can see that taking the Euclidean norm of this vector will give us exactly the cost function. That being said, in the matrix form, we'll be writing the cost function for linear regression as 1 over n times the Euclidean norm of the error squared. So that was basically, this is basically our model. And when we are training the model, we are minimizing the mean squared error loss with respect to the parameters of the model. We can, of course, analytically solve this optimization problem. We need to take the gradient and solve it when it's solve the equation when it's equal to 0. You already know that how to take gradients of such functions. It will be equal to this equation here, and the optimal parameters then will look like x transpose x to the power -1 times x transpose y. Okay, seems like everything is perfect. We don't even need some iterative methods for optimization because we have a closed form solution. And but the question is, what could possibly go wrong? So you probably already know that this is not always not always possible or optimal to use these optimal parameters. So can anyone tell me what can go wrong? Yeah, one option would be
metrics
that
could be singular.
Yeah, exactly. That may be one problem. What if it is not? If it's still kind of easy to use? Yeah, the size of the matrix. So X transpose X is a squared matrix where number of rows and columns is equal to number of features. And we know the inversion of a matrix is approximately d cube of complexity. Of course, we can do slightly better, but that's still, if you have a lot of features, that's still a problem. And also, as some of you already mentioned, the matrix can be degenerate. If you do have linearly dependent features, then you don't have the inverse at all. Or it can be ill conditioned. If you have highly correlated features, then these computing the inverse may be a very unstable operation, which is, of course, also a problem for us. So what can we do with that? Firstly, we don't actually need to use closed form solution. We know nice iterative algorithms that we discussed last week. And if we use gradient descent, for example, to optimize, we don't need inversion at all. We just need matrix vector multiplications. Or you can add regularization, which we will also be talking about today a lot. And for example, adding L2 regularization makes inversion more stable because we add positive numbers to the diagonal, but more on that slightly later. Okay, that was the problem with analytical solution, but that's actually not the only problem we have when we train models in machine learning. Another problem that may arise is so-called overfitting. Let us consider a toy example to illustrate what's overfit and what does it mean for us. The toy example will be the following. We have only one feature. You see it on the x-axis and the target variable, which is a real number. You observe a sample from the orange function. So orange line is the correct functional dependency between x and y, but you observe only some noisy observations, these blue points on the plot. So what we can do, we can feed a linear regression with one feature. The model will look like this. That's W1 plus W2 X. And if you plot the resulting model, it will look like a green line here. But doesn't seem like a perfect model for this data set. So what we can do to improve it? Well, let us add some polynomial features. So let us also include x squared, x cubed, and x to the power of 4 as features. We can still plot this function in 2D, which is awesome. And in this case, we do observe much better model, almost perfectly fits the orange line. Okay, but what then if we use even more features? Maybe it will get even better. Well, it turns out if I keep increasing number of features, for example, if I train linear regression of polynomial regression, it's sometimes called of power 10, you will see that the resulting function, which is a green line here again, it looks pretty bad. Yes, and
do the slides change? Because I still see the red line.
Yeah.
Oh, sorry.
And, yeah.
Do you see it now?
Yes, now it's much better.
Okay, let's. Okay, I have to keep the mouse on the screen. Got it. Sorry. So yeah, we had the linear regression with one feature, then oops. Then if we use when we use add features x squared, x cubed, and x to the power 4, we get this line. And finally, we add even more features, and the line starts looking like this. It has this weird behavior, especially in the places when you don't have a lot of points. So this problem, as Alexander correctly mentioned in the chat, is called overfitting. And it happens when your model that you've chosen is basically too complex for the data that you have. And what we start observing is that our model, it starts to kind of memorizing the training data set or try to perfectly fit the training data, but the generalizability, so how the model will perform on unseen data, becomes really poor. So how do we track it? So the first thing we can look at is the error of a model, right? When we train, we use some data. Let's compute the error of a model on this data. You can see it on the titles of a plot. I hope it's not too small. If something wrong with the presentation, let me know. I can zoom in, zoom out, and so on. So we see that the training error or mean squared error on blue points, it used to be 25 for simple linear regression, then it was around 3 for the middle one, and then it gets even smaller for the last one. So that gives us one more clue that using a training error as a way to measure how good the model is actually a very bad idea. Instead, what people do, and that's something we started talking about in the first lecture, we look at the so-called validation dataset, holdout dataset. That's some points that you've never observed while training. And if you can see here, we now have not only dark blue points, but also the teal points here. And if we compute the mean squared error on these new points, the picture looks much better in terms that it corresponds to our intuition. We see that validation error of the first model is 67, and validation means computed on validation dataset. For the middle one, it's 12, and for the last one, it's 72,000. So now we see that based on validation error, the middle model is the best one out of these three, and that's also what we observe from the two-dimensional plot. And that is for models for which we can't plot this line, this green line and orange line itself. Using the validation set to see, to detect overfitting and to compare different models is actually a way to go. So we can also see how the error behaves when we keep increasing complexity of a model. In this simple example, complexity is just how many features we add, how many polynomials we add to the model. But in general case, it may be how many, you can also, if you have more than one feature, you can add their products, you can raise them to different powers, you can think of any even more sophisticated features which you create out of the initial ones and so on. So as we increase the complexity of the model, and here on the x-axis is basically amount of polynomial features, and on the y-axis we have the mean squared error. The train error, which is the blue line.
You can see the graph. We see like a half of it.
Okay. And like this?
Now it's okay.
Okay. So the blue line, which is a train error, I hope it's not as small as for you. It keeps decreasing when they increase the complexity, even though at some point we know that the model starts behaving pretty weirdly. The orange line, on the other hand, it's for some time in the beginning, it decreases. That means that when the model is very, very simple, it's not capable of capturing the complexity that we need. That is nonlinear dependency between x and y. But then at some point, when the power becomes too large, this test error, it just jumps to the infinity, and I had to crop the plot so that we can see at least something on it. So, like in ideal case, we would like to find the model that minimizes the test error. The test error is basically the proxy on how the model will behave in the real world, right? But of course, we can't try every model in the real world, right? Imagine that you are working in a company, or you're making a model for someone who works in the company, and you can't just give them every model that you trained and say them, please try it out there in the real world, and then say me how well it works. Instead, we need something that will resemble the real world data, and we will call this validation data set. And we hope that the best model on the validation will be also the best model on the test. Usually on on examples that we will be using during the course, you will have both validation and test data given to you. But for example, if we are talking about Kaggle dataset, the test for the test data, you have only the features, but you don't have correct predictions, so that you have to upload the model to on the platform to get your error, and you only see part of it, and so on. So basically, while training models and comparing them and seeing how good they generalize, we're working with training data and validation data. And test data is something that you only work with on the last stage of your work, when you are ready and you think you found the best model. Of course, that gives the understanding why validation is important. I mean, the quality of validation is important, because if validation is very small or it doesn't resemble test data, then the performance on the validation will not give you understanding of how the model will perform on the test data. But here, let's, on our toy example, randomly select 30% of observation as validation. We'll just select them randomly from the test data, from the trained data, and see how these plots with errors, depending on complexity, will behave. So this is what I see. The blue and the green line are almost the same. So the blue line is still train error. The green line is test error, the same one we had. And now we have also the orange line, which is validation. So what we will be doing, we will be selecting the best model based on the orange line, validation. So it will be model either with polynomial power 4, 5, or 6. I can't see from here which one is better. Anyway, so we will select based on that and hope that this model will also correspond to the best model on the test data set, which, as we can see from the green line, may not be the perfect solution, right? So we can say, for example, that based on the test data, the best model will be here with polynomial power 3. That validation gives us polynomial power 4, but still approximately that's a nice proxy to have, given that the test is not available. Okay, that was the way how we basically observe overfitting or detect overfitting. But how can we fight with that, right? So we've seen how we can tune complexity. So basically see how the performance changes with the complexity. But what if you have a lot of features and model overfits and you don't know what happens, right? So if you have 1,000 features and you observe overfitting, so the performance on validation is much worse than performance on the trained data, what should you do? Which feature should you remove? Or how to decrease complexity of the model? One way to do that, and one way to basically make it more or less automatically, is to apply regularization. And the idea of regularization is pretty straightforward. we used to minimize some cost function, which depends on our weights. So let us add a penalty. Some function which also depends on weights will be pretty simple one with the weight lambda. We will call this lambda regularization coefficient. The purpose of this regularizer is to penalize model for large weights, because large weights correspond to these functions which have high variability and looks like very wiggly curves. That's more like intuition of what happens. How to choose the regularizer? Well, basically there are two ways to go. You can choose other ways, but these two are so-called conventional ones that are mostly used in practice. They are L1 and L2 norms. L1 norm is just sum of absolute values of your weights, and L2 norm squared is sum of squares of the weights. So again, we have our cost function, and instead of optimizing the cost function itself, we optimize cost function plus the penalty, which is either sum of absolute values of weights or sum of squares. When coupled with the mean squared error cost function, a specific one, we have two models which have their distinct names, namely ridge regression and lasso regression. And today we will discuss both of them in details and see what properties do they have, why do they have these properties, and how they behave on real data. So let us start with L2 regularization. There are many ways how you can name them, models with L2 regularization. If you want to sound like a statistician, you can say that you're using Tikhonov regularization. If you're a machine learner, you would say ridge regression. If you're a deep learner, you would probably say weight decay. And if you're Bayesian, you will say that's a Gaussian prior on the weights. But all of that burns down to the same thing. And that's what we'll be talking about today. So ridge regression, we have our quadratic loss and the penalty. So let's, to begin with, find a closed form solution for such model. What do we need to do for that? Well, we need to find the gradient of our f. You see what I'm writing, right?
Yes.
Yes.
Okay. The gradient, sorry. So the gradient would be 2 times x transpose times xw minus y. So this is the gradient of the MSE loss. And you also need to take the gradient of the second part of the loss, which is the quadratic regularization, 2 times lambda w. And we need to solve when this guy is equal to 0. So let's divide both parts by 2 and open all the brackets. We will have x transpose xw minus x transpose y plus lambda w equal to 0. On the left, we'll leave everything which has w. That will be x transpose x plus lambda times identity matrix multiplied by w. And on the right, we are left with x transpose y. And we only need to multiply by this guy to the power minus 1 from the left, which will give us the ridge solution for the weights. So that would be x transpose x plus lambda identity to the power minus 1 times and x transpose y. So what's cool about that? Now that we are inversing not x transpose x, but x transpose x plus lambda I, which means that it will be more stable even if X transpose X is ill conditioned. But of course, it still has the same complexity as it used to have, but we can again use gradient descent if we're willing to. So that's the same one, the same formulas, but typesets. Okay, but what about properties of rich regression? So we know that solution looks like this. That's awesome, but what does it mean for us, except for the fact that inversion is more stable? Why would we use it in the first place? So the main property that rich regression brings us is shrinkage. It basically meaning that it shrinks all the coefficient compared to what they would be if we just used simple regression with mean squared error loss. And let's try to gain an intuition why that happens. To do that, let's assume that our features are orthogonal, namely that X transpose X is equal to identity. We can do that by just linearly, using a linear operator. So if you just create new features which are linear combination of the old one, you can find such desired metrics that would satisfy this condition. Solution of unregularized regression in this case would be just X transpose Y. Well, because this guy here is now an identity, inverse of the identity is still an identity, so the solution is X transpose Y. So what about the rich solution? So let's take a look at what we got here. So if X transpose X is identity matrix, then this guy here is of course identity. Then we have identity plus lambda times identity to the power -1. That would be 1 plus lambda times identity matrix to the power -1 times X transpose Y. We know that this guy here is not beta. W. I will call it OLS, ordinary least squares, namely the optimal weights without regularization. So we can basically say that this guy here is just 1 divided by 1 times lambda, because—
Can you scroll down, please?
Yeah, sure. I wish I could, but I can move. Where's the scissors? No, for some reason I can't. But okay, let me write it just on top of that so that you can see. So this guy here, including the inverse, will be equal to 1 divided by 1 plus lambda times the identity matrix. And that is multiplied by X transpose Y, which is equal to, yeah, I'm trying to do control minus, but that's, as you see, only zooms out the menu part, but not the one that I'm writing on. So that's not helping a lot. But that's weird. You don't see the whole slide?
Yes.
Times W OLS. So you see this line, right? I will not write below.
Yes.
Okay, but that's actually all I wanted to write. So, namely, the optimal parameters for regression in case of orthogonal features, that just parameters of ordinal linear regression without regularization divided by 1 plus lambda. So what happened is we took our original weights and we shrunk them or made them smaller by the factor 1 plus lambda. And if you remember, we said at the very beginning that we're only using lambda larger than 0. So this part here is always larger than 1. So it is always a shrinkage operation. So let's see on the example, what does it mean for us? So consider a very simple problem where you're predicting diabetes progression measured by some medical feature, and you have 10 numerical features that you are using to predict this diabetes progression. So let's see how the coefficient of the ridge regression will behave when we're using different values of lambda. We will start from lambda equal to 0, and that corresponds to the simple linear regression. On the x-axis, you see names of the features that we've used, and the bar basically shows us the value of coefficient. If the bar looks upwards, then the coefficient is positive. If the bar looks downwards, then the coefficient was negative. And then we start increasing the lambda. Yeah.
Can I ask a question, please?
Of course.
Can you please say what is shrinkage in Russian, just to describe it in Russian? You said that ridge regression, it's with the help of lambda, it does shrinkage, and shrinkage is translated into Russian as usadka, and as far as I see. And can you just repeat the same explanation, yes, for this slide, but in Russian, to make it a bit more clear?
So I'm trying to think of a proper Russian translation now, but I actually can't. So the idea is that the wave becomes...
Сжатие.
Сжатие. Yeah, сжатие is a
Да,
nice
может
one.
быть, сжатие.
То есть по-русски все веса пропорционально уменьшаются на фактор 1 плюс лямбда. Вы просто взяли изначальный вес, который у вас был у линейной регрессии, вы поделили его на 1 плюс лямбда, то есть он стал меньше в 1 плюс лямбда раз.
Да,
И это называется эффект shrinkage. Или, да, как правильно заметил кто-то, не успел увидеть кто, наверное, по-русски это можно назвать сжатие.
То есть в итоге у нас все коэффициенты будут в каком-то отрезке? Только вот в этом отрезке?
Ну, они
Нет,
все пропорционально уменьшатся.
Мы их не помещаем в какой-то конкретный отрезок, да, мы их просто уменьшаем на 1 плюс лямбда.
То есть вы берете все веса и делите их на 1 плюс лямбда. То есть они все в 1 плюс лямбда раз уменьшились. Ну, это в идеальном случае, когда у нас сечи ортогональны. Вот. На практике вы не ортогонализируете матрицу сечей, поэтому не совсем такая идеальная формула будет работать, но идейно это то, что будет происходить. То есть веса, и сейчас мы это увидим, собственно, на примере. В следующем слайде веса будут все пропорционально сжиматься. So let's return to our example to see how shrinkage happens and what does it mean for us. So we used to have our initial model with lambda 0 equal to 0. It was here. We can see the values of all the coefficients. They are almost all non-zero except for h, which seem to be a very useless feature. And now we start increasing lambda. So firstly, we train model with lambda equal to 0.1. And you can just compare the height of each bar on the second plot to this height of the bar on the first plot. For example, let's take a look at the feature S5. It used to be pretty high. So it's almost last bar. But when we added lambda 0.1, the value of the feature became the value of coefficient for this feature, it was reduced. And if you compare it to other features, you can basically see that all of them were reduced by some factor. they were probably not reduced by this by the same factor, but they all became smaller. If we then go to lambda equal to 1, we observe that the amount of shrinkage, so how much the weights become smaller, increases. So basically on the third plot with lambda equal to 1, all the weights became even smaller. And on the last plot where lambda is equal to 10, so we train model with a very strong regularization, almost all weights are close to 0. But what is important here is we observe that they are still non-zero, right? So they are shrinking, they are all becoming smaller and smaller, but they are not becoming exactly 0 in most cases.
Wasn't they supposed to shrink by the same amount? Like by... Ну, типа на 0,1 все должны были уменьшиться, нет? Потому что было, S1 было большим, а стало меньше, чем X.
If the features were orthogonal, so if this condition holds that X transpose X equal to identity, then yes. But since here we were not orthogonalizing features, that's not happening. That's why they're not shrinking exactly by the same factor. But they do, but they do all shrink somehow. But how they shrink depends on their, basically on their importance for the model. So the difference here with this orthogonal case is we will also account for how large the feature contributes to the model performance. If it contributes nicely, so if it's a very important feature, then probably the shrinkage will be smaller. If the feature was not really useful, then it might shrink much more. The coefficient might shrink much more. Any other questions for Rich? Okay, let's move on.
So yes, there is a question about RIDGE. It's still unclear how regularization helps us. So we shrinked the weights, and what does it give us?
Yeah, I didn't make the plot, but basically the first effect is indeed that the weights become smaller, and you do now have more stable inversion, right? Because of the formula for optimal weights that we had in here. So now just computing the weights is a more stable operation. That was first thing. And the second thing, it's now, it helps with fighting overfitting, because you're basically not, you're punishing your model for becoming more complex. You're punishing your model to have many large weights, which correspond to this function, which basically changes a lot from point to point. When you regularize it, you basically smooth the line, you make the line smoother, and it's harder for the model to overfit. And the larger your lambda is, the harder it is.
Then can we say that L2 or L1 regularized models are always better, always perform better than just pure linear regression? Are there any cases when linear regression without regularization is better applied to our data?
It highly depends on the lambda that you choose, firstly. So you have to properly choose lambda, because, for example, if your lambda is too large, and for example, lambda equal to 10 results in a very small coefficient for all the features. And in terms of performance, that may mean that your model is too simple. So it's like a super smooth line, and it's not able to capture the real dependency. So it's not capturing all the non-linearities in your data. When the linear regression is better, well, when you did not perfectly tune the lambda, and in this case, probably not using regularization would be better. Also, if your model is perfect in some sense, so if your real dependency is linear and all the features are relevant and you don't have highly correlated features, so everything nice, then you don't need regularization, of course, because linear regression would perfectly work. But in practice, in most cases, having regularization is better than not having it.
Okay, thank you very much. Yeah, it's clear.
But tuning lambda is super important, and I think on the next practical session you will practice with that a bit more. Okay, let us then turn to L1 regularization, which corresponds to loss regression if coupled with mean squared error loss. We now have very similar objective. We have our MSE part, and we now have the regularization, which is sum of absolute value. And here comes the problem, because we have sum of absolute value, and how to find the closed form solution is already not an obvious thing. So let us discuss, firstly, in case of orthogonal features, what would be the solution? And then we will see how that gives us an easy way to get a gradient update for such model. So we start from the orthogonal feature case. That's the same formulation. We again will be using the fact that now the weights of non-regularized model is X transpose Y. And let me try to derive that for loss regression. So let's start from the objective. So if I just rewrite the Euclidean norm, it will be XW minus Y transpose times XW minus Y plus lambda times our regularizer. So we'll be minimizing with respect to lambda, and let's start opening the brackets right away. So we'll have W transpose X transpose XW minus 2 times W transpose X transpose Y plus Y transpose Y. So here I just opened the first brackets and plus my regularizer. See what we got here. Firstly, this thing here is identity matrix by our assumption. Second, this guy does not depend on W, and since we're minimizing with respect to W, we can forget about it. And we also know that this guy here is optimal for non-regularized model. So let's write all that down. So we now have W transpose W minus 2W transpose W ordinarily or less, and plus lambda times L1 norm. So what is cool with this formulation is that now we can rewrite all this thing as one sum. Let me show what I mean here. That's minimum over W. Sum for I from 1 to D. That's number of coefficients in W. So this guy here is just of sum of squares, right? So it's WI squared minus 2 times WI times WI non-regularized plus lambda times absolute value of WI. Right, so we don't have any terms that have that take into account the intersection of coefficients, and that means that we can basically solve optimization problem for which component of a vector separately. And this we can do basically right away. Not right away, but we can do it straightforwardly by considering two cases. Because the main problem here was in this absolute value. It's not trivial how to take a derivative and set it equal to 0. But when we have separate equation for each coordinate, we can just manually consider two cases. Wi is larger than 0 and wi is smaller than 0, and see what will be the optimal in both cases. So let me consider one as an example, and for the second one, I will just write an answer. So we consider only one component of the vector, and the first case will be when wi is larger than 0. In this case, our optimization problem will be minimum over wi of wi squared minus 2 times wi OLS plus lambda times wi. So this is a quadratic function, and we know what's the minimum value, but don't forget to take into account condition that wi is larger than 0. So we also have two cases. So the parabola that corresponds to this function looks like this. So we have, it goes through 0 because it's wi times wi minus 2. So it goes through 0 and through point 2 wi or less minus lambda. If this second root is positive, then the parabola will look like this. And the minimum will be this value here. If otherwise the second root is negative, then the parabola looks like this. And since we're considering only the right part of the space, so only this one, the optimum for the second case will be exactly 0. So that gives us a solution for optimal wi in this case. It is 0 if the second root, which is 2 times wi OLS minus lambda, is smaller than 0. And it will be this minimum here, or the minimum of the quadratic function, which is wi OLS minus lambda divided by 2. If the second root is positive, so if 2 times wi OLS minus lambda is positive. Okay, so that was the first case. Now we need to consider the second one when wi is smaller than 0. And here we'll get exactly the same two steps. We'll have a quadratic function. You will need to consider either second root is on the right or on the left. And depending on that, you will have the values of w. So let's see the result that we get. So this is the same derivation. So we reroute our objectives, so it only depends on each coordinate separately. And we want to consider two cases, the positive w and the negative w, to get rid of the absolute value. So for the positive one, we just did the solution. It will be, the weight will be 0 if solution in OLS was smaller than lambda divided by 2, and it will be equal to OLS minus lambda divided by 2 if it was larger than lambda divided by 2. And the solution for the negative one looks super similar. But let us see how that combines together and what it gives us as a final solution. So altogether, we have the following result. We have that optimal coefficient for Laster regression is equal to 0 if the corresponding coefficient was between minus lambda divided by 2 and plus lambda divided by 2. What does that mean? So if in a non-regularized model, some coefficient was pretty small. So it was in the region around 0, where size of the region is controlled by our parameter lambda. Then last regression will be just shrink this coefficient to exactly 0. If otherwise, the coefficient lies on the right or on the left from this region, then it will shrink it, but not in multiplicative sense, but in additive sense. So if the coefficient was on the left, so if it was smaller than minus lambda divided by 2, then we will add lambda divided by 2. So we'll move it slightly closer to 0. If it was on the right, so if it was positive and larger than lambda divided by 2, then we will subtract lambda divided by 2. That is, again, move it slightly closer to 0 from the other side. So that's the intuition of what's happening with last regression. We're again shrinking the weights, but we also have this region around 0 where all the weights are exactly 0. Okay, that was orthogonal case. What happens in non-orthogonal? Does that holds? Well, actually that does. And if you remember the previous lecture, Evgeny told you about proximal update, where on each iteration of your iterative optimization scheme, you are basically solving this optimization problem. So W on the next step will be solution of this optimization problem that you see here. And you can notice if J of W is exactly 0, so if you don't have regularization, then that corresponds to simple gradient descent method. But in our case, we do have this extra non-convex part in our objective. Oops. Sorry. We do have this non-convex G in our objective, and therefore we'll have to solve this optimization problem. Turns out it will look almost the same as the one we've just solved for orthogonal case, and I'll leave it for you as a home exercise to do that in detail, but let me briefly show you what happens there. So let's rename this large part that we have inside the Euclidean norm as A of WK, this one here, because it doesn't depend on W that we're optimizing with but it does only depend on W from the previous iteration. So we need to optimize this objective. We will again open the brackets. So we will say that W minus A of WK is this thing here, sum of these three components, where the third one does not depend on W, so we can get rid of it, plus our regularizer. And this is again only depends on each coordinate separately, so we can rewrite it as a sum and do all things exactly the same as we just did. So consider two cases where Wi is positive, Wi is negative, see where are the roots on the left or on the right, and find the optimum. And the solution will again be W on the iteration k plus 1 is either equal to 0 if A of WK lies within the region, and it will be equal to A plus or minus lambda divided by 2 if it lies outside. So let's try to understand what that means intuitively one more time so that you definitely understand. So recall what was A of WK. It was basically a gradient step of this simple gradient descent. W minus lambda times gradient. So where we end up if we make a gradient step from WK in the direction of the gradient. If after this step, so if the value of A of WK is closer to 0, is close to 0 in terms of lambda, so it lies within this region from minus lambda divided by 2 to plus lambda divided by 2, then we zero out. So then in this gradient step, we say that this coefficient goes exactly to 0. If after the step we don't go inside this small region around 0, then we shrink the coefficient. So that's exactly what we had in the orthogonal case, but there we had just one step. we said we have non-regularized weights, and we either set them to 0 or shrink them by additive factor. Here we do the same thing, but on each step of our iterative optimization algorithm. On each step, we either zero a coefficient out or shrink it, or make a gradient step and then shrink it by the factor lambda divided by 2. But we do that iteratively until the model converges to a local minima. That basically why the Lasso regression is called selection operator, because after training the model with Lasso, you not only shrink the coefficients, so you regularize the model so the coefficients are not very large, but also some of the coefficients becomes exactly 0, meaning that you basically select only the most relevant features. And those features that are considered not relevant, they get the weight 0, and you can throw them away from your model. So let's consider the same example we had with the ridge regression, but now with the Lasso, and see again how the weights behave when we increase the value of lambda. The first plot here is exactly the same as it used to be for ridge. So it's non-regularized regularized model. And now we start increasing lambda. So what we see that large coefficients for S5, for sex, for BMI, and for S1, they are still non-negative, even though for S1 it's like, I mean, not non-negative, they are still not 0, but they all shrink. But at the same time, the coefficients that were initially pretty small, they become exactly 0, even on the second plot where we have small lambda. When we choose lambda equal to 1, we see that almost all the coefficients become 0 except for 2, which are probably the most important. And then if your lambda is very large, it means that this part of your optimization procedure, which corresponds to penalty, it basically overweight, so it becomes more important than minimizing the mean squared error, and as a result, all the coefficients are 0. And your model doesn't work probably at all. But the penalty is super small. So that was a point about L1 regularization. Any questions?
So how do we choose lambda from with which it's better to have a model?
Yeah, that's the next topic I'll be talking about.
Oh.
That we will discuss now. Let's make sure that everyone understands the idea of Lasso and what happens there. So the shrinkage and selection. And if there are no questions, so we'll turn to this. Okay, no questions about Lasso. Let's move on. So yeah, as it was correctly asked, we still don't know how to properly choose lambda. But let us think what lambda is. Lambda is hyperparameter, so it's a value that you need to define before training. So we can say that models with different values of lambda are basically different models, right? So you have, for example, simple regression with lambda equal to 0. Then you have ridge regression with lambda equal to 0.1. Then you have ridge regression with lambda equal to 1, and so on. And you have also lossy regression with all possible lambdas. And as usually is in practice, you have no idea which of them is better. And this brings us to the question how to compare different models. So how to compare simple regression, Lasso with lambda equal to 0.1, Lasso with lambda is equal to 1, ridge with 0.1, and so on, with all these models. So we already mentioned, briefly mentioned validation. Now we'll talk about validation and cross-validation in more details. So here's what we have. We have our training data, and we have a bunch of models. Let's assume that we have 3 of them. Let's assume that we are training only rich regression, and we have 3 candidates for the best lambda. On practice, you would try much more lambdas because it's you never know which one is better. So you would probably tune even more. But let's, for simplicity of an example, assume that you have chosen 3 and you want to choose the best out of them. We know that the wrong way to do it would be to train the model, compute error on trained data, and compare these errors on the trained data. We know it's a bad way because if the model overfits, it will have super small error on the trained data, but it doesn't mean that the model is good. Instead, we would take part of the training data set. We will call it a validation. We will not use it during training. So we will train on this first part, which is called training data, and then compute error on the validation data set and compare these 2 numbers. So basically, you will have to train 3 models, model 1 to 3, compute 3 validation errors, 1 to 3, choose the smallest one, and then you have the model with the best lambda out of these 3. But then the question would be, how to choose a good validation data set? Let's, for example, consider the 2 examples from the very beginning of the lecture, where we had a 2-dimensional problem. And assume that you've split your data into train and validation in the following way. So you have all numbers all values that are on the left from the x equals to 0, they go to the trained data, and then all numbers that go to the right from the x equal to 0, they go to validation. Of course, it's not likely that you will do that on purpose, but such errors, they happen, especially if you're creating validation set manually. And for example, you say, okay, I will just take first 100 observations as train, then the last 100 observations as validation, and then found out that the observations were sorted in your data set. So why would that bad? Would that be bad? Well, if you train your model on such trained data set, it will be awfully bad, even though in general, the model may not be that bad, because if you train it on the whole data that contain all x's possible, we know that this model worked nicely. It nicely fitted the orange curve, or we've seen it. But because you firstly chose bad trained data and bad validation, so they are totally different, the value of your loss on the validation will be super bad, and the training error and the validation error will not be a good indicator of how good the model is. So that's the first thing to remember, is that be careful when creating a validation data set. You would want to randomly pick points from your training data, and you want this validation data set to be large enough. Because if you have 2 observations in your validation data set and they happened to be in some weird places, they also will not be good indicators of how good or how bad your model is. So that brings us to the second way how we can validate models. It is based on the idea that best validation data set is the whole training data, right? If my validation was as large as a training data set, but at the same time, we will not use the same data for training and validation, that would be perfect. So let's try to think of the way how we can achieve that, how we can obtain a validation that is as good as the whole training data that we have in the beginning. And that is called cross-validation. The basic type of validation is called k-fold cross-validation, but there are other more sophisticated as stratified cross-validation, groups for cross-validation, and so on. But as soon as you understand this simple concept, everything else will be straightforward. So what happens in k-fold cross-validation? We take our data set and we split it into k parts, and usually they are called folds. The first fold, the second fold, and so on. That's just k parts of the data set of the same size. And what we start to do, we start to use each part of the data set as the validation one by one. For example, we start from the first fault. We remove it from the training data because we say this will be our validation. We train on the fault from the second to the last one and evaluate model on the first fault. And we obtain mean squared error on the first fault and call it MSE1. Then we do the same for the second fault. We take the second fault from the data, we put it outside, we don't touch it. We train model on all the other faults. So the fault number 1, number 3, fault number K. We again train on these K-1 faults and we test on the second one. We obtain the second mean squared error. We do the same thing for fault number 3, fault number 4, and so on, and for fault number K. And again, for fault number K, we again train on first K-1 faults, and then we validate or compute error on the last one. So as a result, for one model, we obtain K numbers. So in order to compare different models to each other, we will basically average MSE on all the faults. And this will be, we will call this, for example, if we're talking about linear regression with MSE loss, we will call this mean squared error loss on K-fault cross-validation. And it will be the number that indicates how model 1 performs on cross-validation. Then we do the same one for model number 2, for example, model with the different lambda. And we again computed its mean squared error on cross-validation. And then this cross-validated error is used as a comparison. Why this is good? Well, that we see that in the end, after we obtained these K errors, we basically used all the data that we have in the training data set was used as validation, and at the same time, we did not the train and validation were not overlapping in each iteration separately. That's super cool. That's an interesting concept, but of course it has some peculiarities. So to sum up, what has just happened? So we've split our dataset into K parts. For each model that we want to evaluate, we compute the value of the cost function on each of K validation parts, meaning that we need to feed our model K times, right? So when we remove first part as validation, we feed model on rest and validate on the first one. Then we remove the second one. We again have to train model from scratch and validate on the second fault, and so on. Then we average these K numbers, and this resulting number is used to compare all the models that we want to compare and choose the best one. So first thing first is don't forget that you do have to train model K times in most cases. And if you have many models and your K is large, that may take time. And you can try during the practicals, you will be showed how to use cross-validation scikit-learn. Just try to set K to a very large number and include, I don't know, 20 or 100 models and see how long it will take to compare all of them. At the same time, if K is very small, then your validation will be too large and training will be too small, right? So if your K is equal to 2, then you split your dataset into 2 parts. And that means that you basically remove half of the observation from training every time, which not always a good thing to do, because if half of the observation is not a lot and you have a lot of features, then the overfitting will be pretty bad. So we do want large enough number of faults, but at the same time, we don't want to retrain the model too many times. So there is always this trade-off between how large the K is and how much you want to, how much you're ready to wait until the best model is chosen. And this is of course up to you, and it also depends on how fast your computer is and how nicely you tuned or chosen the models to compare, and so on. There's one specific case. So like in the limit, you can of course choose number of faults to be equal to the number of observations in your data set. So you every time remove only one object, you train on almost on the whole training data set, which is awesome. So you don't lose a lot of information. Then you test on this one object. Then you remove the second one, you again train on the almost on the whole training data set, and you test, you validate on the second object, and so on. That's of course mean that you have to train your model n times, which is pretty bad. But a good thing is that your metric will be pretty close to what you want it to be. So this method is called leave one out cross-validation. So every time you leave one object, but it's again a special case of k-fold cross-validation. The good thing about linear regression is that there is actually a closed form solution or closed form formula for leave one out cross-validation for regression with MSE loss, meaning that you don't have to retrain your linear regression n times. So you only need to compute x transpose x to the power -1 once, and then you need to just sum n components based on this formula. I will post the derivation of this formula, and also for rich regression you can also derive a very similar thing. So that's a good thing to remember, that you actually can obtain leave one out cross-validation error for linear regression without training the model n times, which is pretty cool. Oops. Okay, so that brings us to the end of my today's talk. Let me remind you the objectives that you see on the slide. So we talked about closed form solution for linear regression. We discussed properties of linear regression with L1 and L2 regularization. What's cool about regularization, it helps with overfitting. So it basically restricts your model or penalizes the model for having large weights. And at the same time, lasso regression also basically throws away the irrelevant features by setting their coefficients to 0. And we also talked about validation, which we can use to compare models with different hyperparameters or just different models, and cross-validation as the way to do the same thing, but in a slightly more sophisticated manner when you're using all the training data for validation as well. Any questions? Do we have shared weights during cross-validation? No, in general, the concept is that you've chosen number of faults, and for each fault, you train your model independently, so to say. So you train your model on without the first fault, you predict on the validation and compute the error. Then you retrain, so you train from scratch on another part of the data, and then you predict on the second fault and compute the error. So like in general, we do that independently. But for example, for linear regression, we can show that is identical to just computing x transpose x to the power -1 once, and then plugging in the formula. So you don't need to recompute it n times. But for a general model, if you don't know the formula, how to compute the cross-validation error in a closed form, which is almost always the case, except for these very simple models, the model on each fold don't know anything about other models, which were trained for during cross-validation. Okay. If there are no questions, I will post the slides today, and also this. So these slides is basically a notebook, so that you can, if you're interested, you can go through the code and see, for example, how I trained last sandwich and blah blah blah. But I'm pretty sure that on the nearest practical, you will more interesting examples and practice with both with regularization and cross-validation. So yeah. Thank you all for attention. If you still have questions, I'm here for some time. If you don't have questions, then thanks for coming. Have a nice weekend.
Thanks. Goodbye.
Thanks.
Thanks.
Thank you.